we finally have data. The United States Navy has admitted that yes, there are hours of videotapes. We now realize that these objects, whatever they are, can travel up to Mach 20. When you calculate the centrifugal force inside the rocket ship, you realize that any living thing would be crushed by the zigzagging of these objects, whatever they are. We're talking about a new law of engineering beyond anything that we can muster here on the planet Earth.
For 17 straight hours, a space telescope watched something no one expected to see. A faint X-ray glow stretching nearly 400,000 kilometers across space, surrounding an object that had crossed into our solar system from another star. No interstellar visitor had ever done this before. Not Oumuamua, not Borisov. Yet there it was. NASA calls the object 3IATLAS, a comet. But the data tell a story that isn't so easily dismissed. A first in X-ray astronomy. And quick aside, before this gets even stranger, if you're enjoying this kind of deep space mystery, tapping the like button, subscribing, and clicking the notification bell is the easiest way to keep these stories coming. It's free, it takes literally a second, the YouTube algorithm absolutely loves it, and it's honestly the best way to support the channel without launching your own space telescope. Much appreciated. Between November 26th and November 28th, 2025, Japan's XRISM mission carried out an unprecedented observation. Over a 17-hour exposure, mission operators repeatedly adjusted the spacecraft's orientation 14 separate times to keep the fast-moving object centered as Earth itself drifted through space. This wasn't a passive observation. Engineers tracked 3IATLAS in real time, compensating for both its velocity and the motion of the observatory. X-ray's soft X-ray imager filtered out cosmic rays, solar scatter, and background galactic noise. When the data were processed, the result was unmistakable. A diffuse X-ray halo extending nearly 1/3 of the distance between Earth and the Moon. JAXA independently verified the signal. Background models were run, instrument artifacts ruled out. The measurement held. This was the first confirmed X-ray detection of an interstellar object. Before we go further, I'm genuinely curious how this strikes you so far. Do you think this kind of X-ray emission can still be explained by an extreme but natural comet process? Or does it already feel like we're stretching existing models a bit too far? Drop your thoughts in the comments. We really do read as many as we can. We especially appreciate thoughtful, constructive takes. And more than once, your comments have shaped future videos. Why that matters X-ray emission from comets isn't unheard of, but only among native solar system comets, where solar wind ions interact with neutral gas through a process called charge exchange. Interstellar objects were different. Oumuamua showed nothing. Borisov, despite deep observations by Chandra and XMM Newton, stayed dark. 3IATLAS broke that pattern, and it wasn't subtle. The sheer scale of the glow implied a gas cloud, vastly larger than anything previously observed around an interstellar visitor. Whatever 3IATLAS was doing, it didn't fit existing models. A comet that behaves. Wrong, Hubble had been watching too. When it first imaged 3IATLAS in July 2025, it showed a familiar cometary coma, but its shape was wrong. Instead of a symmetrical cloud, the coma stretched into a sharp teardrop, aligned precisely with the object's motion. Once Corbin and his colleagues found the coma, they said that its shape looked odd, instead of balanced, and the top of the coma was impressive. Over the next 4 months, the structure evolved dramatically. The leading edge sharpened, the tail curved and fanned out. Subtle striations appeared, possible jets or localized eruptions, yet the overall geometry remained unusually stable. The scale was enormous, hundreds of thousands of kilometers, and yet chemically, something didn't add up. James Webb finds a dry comet. When the James Webb Space Telescope examined 3IATLAS in infrared, the results surprised nearly everyone. Water, normally the dominant driver of comet activity, barely registered. Instead, the coma was dominated by carbon dioxide, 87%, with carbon monoxide, 9%, and just 4% water. Solar system comets typically show the reverse. Even stranger were the metallic signatures. Nickel appeared in unusually high abundance, outpacing iron by a wide margin. On official plots, the ratio stood out as an extreme outlier. Some researchers, including Harvard's Avi Loeb, noted the pattern resembled certain nickel-rich industrial alloys. Others urged caution. The numbers were real, but interpretation remained open. What couldn't be ignored was the paradox, a dry comet producing extreme activity. This is another point where I'd really like to hear your take. If you were building the model, which part bothers you more? The lack of water, the nickel abundance, or the sheer level of activity despite both? Let us know in the comments. We actively read them. In orbit that refused to behave as 3IATLAS approached the Sun, orbit analysts at NASA's Jet Propulsion Laboratory noticed something else. Its trajectory refused to behave. Hundreds of positional measurements collected from ground-based observatories, space telescopes, and radio arrays across the globe were folded into increasingly refined orbital solutions. Each new data point tightened the model, and yet, the residuals persisted. By late October, the discrepancy had grown too large to ignore. Observations from ALMA placed the comet nearly 4 arcseconds away from its gravity-only prediction, an offset that translates to thousands of kilometers at the object's distance. The mismatch was systematic, not random. When analysts introduced a non-gravitational acceleration term, the fit improved immediately. This correction is standard practice for active comets. This mismatch sharpened the debate. Some researchers argued that outgassing geometry could explain the discrepancy, jets oriented in particularly efficient directions producing strong thrust without proportionally increasing visible mass loss. Others pointed to uncertainties in the comet's size, density, and internal structure, any of which could skew mass estimates. All of these explanations fall within known comet physics. And yet, taken together, they required a carefully tuned set of conditions. Sustained, highly directional outgassing from a body with unusual composition, unusual chemistry, and an interstellar origin. Again, nothing impossible, but not something that fit comfortably within the patterns established by decades of observation. As with the X-ray emission, the color reversal, and the spiral jets, the trajectory anomaly did not stand alone. It added another constraint, another piece of evidence that any complete model of 3IATLAS would have to satisfy. Whether those constraints ultimately point to an exotic natural process or simply an extreme end of known behavior remains an open question. For now, the comet continues on its path, tracked, measured, and increasingly difficult to ignore. A color shift no one expected as 3IATLAS swept through perihelion, solar observatories, stereo, and SOHO detected an abrupt and unexpected shift. The comet's color changed. What had been a dusty red coma transformed into a deep blue glow, bluer than the sun itself. For comets approaching perihelion, this is the opposite of what physics predicts. Normally, increased dust production scatters shorter wavelengths, causing comets to redden as they heat up. Here, that trend reversed. Independent ground-based spectroscopy confirmed the change. The spectrum steadily migrated toward shorter wavelengths as the comet rounded the sun, ruling out instrumental error or calibration drift. Then came the polarization data. Light reflected from cometary dust is subtly polarized, and those polarization signatures are well cataloged across decades of observations. 3IATLAS exceeded them all, registering the most extreme negative polarization ever measured, not just among interstellar objects, but across the entire comet record. At the same time, the comet's brightness surged, peaking near magnitude 9. Color, brightness, and polarization shifted in lockstep. These measurements came from different instruments, operated by different teams observing in different wavelengths. Yet, they converged on the same conclusion. Something fundamental had changed in the comet's coma at perihelion. Not a fluctuation, not noise, a real, coordinated transformation unlike anything previously recorded from a comet. Jupiter, a near-perfect alignment. Then came the orbital coincidence. That reignited debate. Trajectory solutions from NASA's Jet Propulsion Laboratory showed that 3IATLAS would pass 53.445 million kilometers from Jupiter. Jupiter's Hill radius, the boundary within which its gravity can dominate over the Sun's, extends to 53.522 million kilometers. The difference was just 57,000 kilometers. On interplanetary scales, that margin is vanishingly small. Planetary flybys are typically discussed in millions of kilometers. Here, the miss distance was smaller than Jupiter's own diameter. To some researchers, this was simply an eyebrow-raising coincidence. To others, it demanded statistical scrutiny. Avi Loeb estimated the probability of such a close match at roughly 1 in 25,000. Not vanishingly small, but far from routine. His argument was not that the passage implied intent, but that it fell into a region of parameter space where chance alone becomes uncomfortable. Then came the orbital coincidence that reignited debate. As ices sublimate, escaping gas produces a small but measurable thrust, the so-called rocket effect, nudging the nucleus off a purely gravitational path. In that sense, nothing unusual was required. What stood out was the scale. The best fit models indicated an acceleration on the order of 8 centimeters per second squared, sustained over multiple weeks and peaking near perihelion. For comparison, many well-studied comets exhibit non-gravitational accelerations an order of magnitude smaller, and often only briefly. According to calculations presented by Avi Loeb, maintaining a force of that magnitude would require the comet to lose a significant fraction of its mass over a relatively short period. Such mass loss typically leaves unmistakable signatures: dramatic brightening, dense dust production, or rapidly evolving coma structure. But while 3IATLAS was clearly active, its observed coma did not fully match the level of erosion implied by the orbital data. From a dynamical perspective, the Hill radius is not just a mathematical boundary. It marks the region where objects can be temporarily captured, redirected, or significantly reshaped by Jupiter's gravity. Comets passing near this threshold can have their orbits altered in subtle but lasting ways, changes that ripple outward across the solar system. If an interstellar object were to experience any measurable gravitational influence from Jupiter without committing to a deep encounter, this is precisely where it would occur. Mainstream planetary scientists urged restraint. With enough interstellar visitors, they argued, rare geometries are inevitable. Hyperbolic trajectories are shaped by countless variables: initial velocity, approach angle, solar gravity, planetary perturbations, and even non-gravitational forces from outgassing. In a sufficiently large sample, improbable alignments ceased to be remarkable. The disagreement was not over the calculations. JPL's numbers were solid. The Hill radius is well defined. The pass distance was real. The debate centered on interpretation. Was this simply a statistical outlier, a coincidence highlighted only because the object itself was already unusual? Or did it represent another data point in a growing pattern of anomalies that resisted easy dismissal? For now, the consensus remained cautious. Jupiter had not captured 3IATLAS. No dramatic deflection was expected. The object would skim the outer edge of Jupiter's gravitational reach and continue on its path. But the precision of the encounter ensured one thing: every shift in trajectory, every deviation from prediction would be measured. As the March 2026 approach draws closer, orbital solutions will tighten. If the path holds, the coincidence will remain just that, a curiosity. If it changes, even slightly, the discussion will reopen. Not because the numbers were wrong, but because in celestial mechanics, rare alignments matter, even when they prove to be nothing more than chance. Spiral jets and a spinning core in December 2025, ground-based images from Spain added another piece to the puzzle. High-resolution observations captured distinct spiral jets, narrow streams of gas and dust unfurling from the nucleus in tight, corkscrew-like arcs. The geometry was unmistakable. These were not random plumes or diffuse outbursts, but structured emissions tracing smooth, repeating curves through space. Such patterns only emerge when an object is rotating, and when active regions on its surface repeatedly vent material as they sweep through sunlight. Each spiral marked the path of a jet carried outward by the comet's spin, preserving a record of the nucleus's rotation rate and orientation. The implication was clear: 3IATLAS possesses a coherent, stable core, not a loose aggregate shedding material chaotically, but a body with localized vents and sustained internal activity. Independent confirmation soon followed from space. The European Space Agency's JUICE spacecraft, monitoring the inner solar system from a different vantage point, detected two distinct tails extending from the comet. One was broad and dust-rich, reflecting sunlight in visible wavelengths. The other was narrower, gas-dominated, and more tightly aligned with the solar wind. The orientation of these twin tails matched the jet structures seen from Earth. Together, the observations painted a consistent picture across scales and instruments. Material was being released from specific regions on the nucleus, separated by composition, and sculpted by both rotation and solar forces into a highly organized system. Spiral jets themselves are not unprecedented. Several solar system comets, such as 67P Churyumov-Gerasimenko, shown similar features when imaged up close by spacecraft. In those cases, the jets were driven by water ice sublimation and mapped to well-understood surface fractures and pits. But 3I-ATLAS does not fit that template. Its chemistry is fundamentally different. Its activity is dominated by carbon dioxide and carbon monoxide, not water. Its orbit is hyperbolic, its origin interstellar, and its jets remain stable and well-definitely despite conditions that would normally disrupt such delicate structures. That combination, spiral jets, extreme dryness, interstellar origin, and sustained coherence, has no clear precedent. It suggests an object whose internal structure and thermal history diverge sharply from the comets formed around our sun. Whatever processes shaped 3I-ATLAS did so in a different environment, under different pressures, and possibly over far longer timescales than those experienced by native solar system bodies. For planetary scientists, the jets are more than a visual curiosity. They are constraints. They limit what models can explain the comet's behavior and force a reevaluation of how interstellar objects store volatiles, conduct heat, and respond to solar energy. As further data from JUICE and other observatories continue to arrive, these spiraling signatures may become the key to understanding not just how 3I-ATLAS behaves, but where and how it was made. So what is 3I-ATLAS? NASA's position is firm: a natural comet behaving unusually, but within the messy boundaries of known physics. No threat, no technology, no reason for alarm. Most astronomers agree, but the list of firsts is undeniable. First interstellar object with X-ray emission, extreme non-gravitational acceleration, dry composition with hyperactivity, record-breaking polarization, near-perfect Jupiter alignment, structured spiral jets, none prove anything exotic. Together, they ensure one thing: certainty is no longer cheap. As 3I-ATLAS approaches Jupiter in 2026, observatories worldwide are watching. The next data release, especially from JUICE, may settle the debate or deepen it. For now, the universe has sent us something unfamiliar, and the story isn't finished yet. If you want to stay with this story as it unfolds, liking the video, subscribing, and turning on the notification bell really does make a difference. It's free, it helps the channel more than you think, and it's the best way to make sure you don't miss the next deep dive when new data drops. And if you know someone who loves space mysteries, feel free to share it with them too.